Hello, Miss Pariseau here. I wanted to go ahead and give you a video here in case you were absent or want to go back and review or fill in notes or whatever. This is a resource for you to refer back to. So we started with our intro to exponential functions. Is we took a look at just the form of the graph, which you can see over here. All right, and we talked just a little bit about just the basics. So this current function that's being graphed is currently the parent function, y equals 2 to the x. And an exponential function is anything that has a variable in the exponent. So just because it has an exponent doesn't mean it's an exponential function. It's if the variable is in the exponential position. All right? So we can see here that our exponential has a y-intercept of 1. Okay, some of our key features, key characteristics about these exponential functions is the y-intercept is 1. And then the other major one that we want to go ahead and graph in here is there's this line that it's approaching. Well, actually, it's as we read from left to right, it's coming away from that line. And that line is called your horizontal asymptote. And sometimes you'll see me abbreviate it just as HA. And the reason for that is because as our x value gets smaller and smaller, right, as we get to more negative numbers, remember negative exponents mean that we are repeatedly dividing. Well, we can't divide by something and get 0. 0 divided by a number will give us 0, but that's the only way. So if we're repeatedly dividing, in this case by this 2, it's just going to get smaller and smaller, and it's going to approach this horizontal line. And in this case, our horizontal asymptote is y equals 0. So those were just some of the basics there. And we can kind of see, too, if we plugged in some points, when I plug in 1 for x, 2 to the first power, that gives me the output of 2. When I plug in 2, I get out of 4. 3, I get out 8, and so on. Right? When we get down to here, when we plug in -1, it's right, 2 to the negative first is really the same thing as 1 over 2, which is 1/2. So we can see that it's about halfway. And anything after that is kind of approximated if we're doing it by hand. So then we took a look at, okay, what's the difference between exponential growth and exponential decay? Well, if you look at all the graphs in the growth section, they do have something in common, right? As you go left to right, notice they're kind of flatlined, and then they either shoot up to positive infinity, or they're, again, starting leveled off, and then they shoot off down to negative infinity. Whereas in the exponential decay, they're actually coming from infinity and leveling off. So either coming from negative infinity and leveling off, or coming from positive infinity and leveling off. But the point here is that we want to be able to recognize these graphs as a growth or a decay. And it's not about the direction on the y value, it's more about where it's approaching, right? Is it leveling off like it does in a decay as we go to the right? Again, we always move, let me put that right. We always are moving from left to right when we read these graphs. Okay, and so the way that I think about this, you can think about slope dude if you want, but I also think about it as if it's a growth, right, the plane is taking off, and it's either taking off and flying north, or perhaps it's taking off and flying south, right? Well, if it's an exponential decay, it's more like the plane is coming in for a landing, right, and kind of it's either flying in from the north, coming in for a landing, or flying in from the south and coming in for a landing. So those are the main features as far as a graph goes for recognizing a growth or a decay. All right. So that would help you out with if you wanted to go over here and just pause the video real quick and take a look at the graphs and determine if they are growth or decay. When you're ready, press play and come back and see how you did. All right, so here's what we should have gotten. Again, if we think about that plane analogy, this plane is taking off, so this is a growth. I'm going to use G for growth, D for decay. For 1B, again, the plane is taking off, so this is a growth. Decay, because as we go to the left, notice it's starting to flatline. It's leveling out. So that's what makes them decays. So those are decays. This is a growth. And this one, it's a little snippet, but you can see that it's a little bit flatter here and then starts to get a little steeper here. So that's where that growth is coming from. All right, now you'll notice that there's some other things that are happening in these graphs, right? Like notice our y-intercepts are changing. They're flipped upside down. They're moved left and right. And that's where we want to come back to this idea of our transformation rules and the impact that they have on our graphs, okay? So if we recall, like first off, these were like just your general transformation rules. So we can plug this into any type of function, quadratic, cubic, and they're all going to do the same thing, these a, b, c, and d values, right? The a and the d value are your stuff that happens to the y's. It's the vertical stuff, okay? Whereas the b and the c values are what happens to your x's. And remember, they're your x for a reason because they always did the opposite of what they look like they were doing. So if we take a look at, and we kind of just go back and just review, this a value, its major impact was that if it was a negative number, it did a flip, okay? It flipped the graph vertically. There's a vertical reflection, a vertical flip, right? It means that it's flipping over the x-axis, okay? Now, the number itself, the value of it, not just the sign, but the number, if the a value was greater than 1, it was a vertical stretch. So think about taking a marshmallow and pulling from the top and the bottom, and you would be stretching out that marshmallow. It would get long and skinny, right? Now, on the exponential graph, it's a little bit harder to see that, but I'll switch over to the Desmos calculator just to show you that. Now, if our a value was between 0 and 1, and again, the reason I'm saying it's not just less than 1 is because remember the negative sign actually tells us if it flips. So basically if it's a fraction, right, it's less than 1 whole. That's going to tell us that, well, all right, well, if we make it greater, it's going to be a stretch. This is where we're going to take our marshmallow and we're going to squish it from the top and bottom. Imagine putting the graham crackers on the top and the bottom, and the other stuff just kind of oozes out the side. So this is going to be a vertical compression. All right, it makes it flatter. All right, whereas this makes it steeper. Trying to think of the mathematical words versus just my marshmallow analogy. Okay, so this is, again, the a value is all about that, is all about the vertical. All right, so let me see if I can, where's my Desmos? Here we go. All right, so I'm going to go over to, let me go ahead and save that real quick. All right, let me close that up. Let me go to our exponential. All right, so the graph in red here represents the parent function, which I'm not going to change. I'm going to go ahead and just change the a value and the b value. So again, that a value, remember when it went negative, oops, I got to change I didn't save it. Let me change my settings here. Negative. There is no value there. Okay, sorry about that. All right, notice what happens when I go into the negative, right? This is what I mean about if it's just a plain old -1. Notice that instead of being at a +2, it's now at a -2. So it's taking the opposite of the y value, okay? And hold on, something's yelling at me here. I want to fix this. -5, there we go. It's not yelling anymore. All right, and then if I go to here, notice if, right, if I get to 0, if a is 0, it just flatlines it. It's completely been squished, okay? So a can't be 0, but notice it's hard to see because it looks like it's kind of being stretched along the x-axis, which in a way it kind of is, but it's actually, imagine like someone pushing down from the top and almost flattening it, right? That's that idea of getting a number that's less than 1. And then on the opposite end, okay, imagine going from the top right here and just pulling it straight up and stretching it. And notice what happens to everything, right? The y value, it was at 1, now it's at 3. So notice my a value, it's 3. I've stretched it. I've done a vertical stretch 3 times, okay? All right, so we can see the impact of the a. Now the d value, right, notice what happens when we change that, okay? That's going to shift, that's a vertical shift. And so that's going to move our graph up and down, all right? And so whatever it is, again, the y value does exactly what it says it's going to do, okay? So if we're coming back over here, this is where I would be making those notes. The d value is a vertical shift. If it's positive, it means that we've taken the whole graph and shifted it up, okay? The main thing that that's going to tell us is that that's going to impacts our horizontal asymptote, right? Okay, so if I go back to that graph real quick, if I can remember where it is. There it is, okay? Notice what happens, right? Currently, my asymptote, it's approaching y equals 0. Well, if all of a sudden I shift the graph up to 1, now my asymptote is approaching 1. If I keep it going, right? Whatever I'm adding or subtracting at the end is what my new asymptote is going to be, okay? All right, so that's going to have that impact on our final equation if we're just reading that equation. Now, your b and your c values, they are happening directly to the x. We're really not going to worry too much about the b value because we're going to talk about that in a different way. But the c value here, we want to pay attention to, and this is where it gets hard on this graph because it's not a symmetrical graph, okay? If I were to go back and let's take a look at the quadratic, right? That one we're familiar with. I'm going to close the exponential for a second, right? If I change that c value, right, we can clearly see that, okay, look at the vertex, I moved it over 3 places to the right. So if it's positive, I'm going to the right. Now, here's the thing. It's going to look like in the equation, it's going to look like -3. So again, it looks like a -3, but it's really that we're taking away that positive 3. And if it was subtracting a negative, it would look like +3. So again, your x's look opposite of what you think should be happening. So if I go back to that exponential here, okay, here it doesn't really look because of how it's moving and the shape of it. It's really hard to see it as moving left or right. But if we take a look at this point right here, and now look where it is. It's 1, 2, 3 places over. But if I were to slide this around, it kind of looks like it's being peeled back from there. When in actuality, it's shifting to the left and to the right. Okay, it's harder to see which ones line up. Okay, so that's a little review of those transformations that we have there. So on the next page, go ahead and pause the video. And what I'd like you to do is what we did in class here was we just said, what are the transformations that are happening? And just make a really quick sketch of what you think it would look like. Right? So go ahead and pause, then press play to come back for the first one, which I'll talk you through. And then the rest, I'll have them done, and you can press play to skip ahead and see those. All right. So if we take a look at the first example here, right, we want to take a look, and they're performed in this order, CBAD. Okay, so you take care of your X stuff that's happening to the X first, then you take care of your vertical flips and stretches, and then you worry about moving them up or down. So I can see here there's no b value. It's staying exactly the same, but I'm -3. So again, it looks like subtracting. So it really means it's moving to the right 3 places. There is no a value out in front. Remember, this is part of the parent function. Okay? And then that +4 means we're going up 4. So if I were to sketch this, right, here's kind of like a bad graph of what the parent function looks like. And if I were to go right 3 places, I'm going to use this kind of as my anchor point. I'm going to go right 3 places, a 1, a 2, a 3, and I'm going to go up 4. I don't know, like something like that. And so I'm going to keep the shape. I'm like, okay, it probably is going to look something like that. All right? So hopefully that gives you an idea of what to look for as we're doing these. But go ahead and pause the video, come back, press play, and check the answers for the rest of these. Okay, go ahead and check those final answers and let me know.